For decades, machine learning hardware relied on a strict physical boundary. CPUs and discrete graphics cards operated in isolated domains with dedicated memory pools. Traditionally, tensor data is manually copied from system RAM, serialized, and shuttled across a narrow PCIe bus to the GPU's VRAM before computation begins. Apple Silicon's unified memory architecture dissolves this boundary, surrounding CPU and GPU cores with one massive high-bandwidth memory pool. This integration happens at the physical die level. Processing units share direct access to the memory pool, bypassing memory copy routines used by hardware-agnostic frameworks. Without isolated hardware components, legacy memory management protocols built for PCIe transfers become completely obsolete. The silicon demands an entirely new software approach. Mature frameworks like PyTorch were hard-coded for the discrete memory paradigm. Their underlying architecture deeply assumes that data must be moved from one physical location to another. When developers run PyTorch on a Mac, they typically use the .toDevice command to shift processing to Apple's Metal performance shaders. This explicit command forces macOS to execute software-level overhead to simulate a physical bus transfer. The framework treats the unified system on a chip as if it were still partitioned by a PCIe bridge. MLX is Apple Machine Learning Research's native solution. Instead of forcing an abstraction layer, MLX discards it entirely to trust a unified architecture. A machine like the Mac Studio can be configured with up to 192 gigabytes of unified memory. Running legacy frameworks leaves a massive percentage of that compute potential bogged down in artificial transfer cycles. Achieving maximum throughput requires abandoning the illusion of discrete memory and adopting a framework that maps exactly to the hardware's physical reality. The core operational philosophy of MLX is zero-copy execution across the unified memory pool. In MLX, instantiated arrays belong strictly to the shared memory pool. To compute, the CPU directs a pointer to that address, reading and writing in place. The GPU then targets the exact same address for the next operation. Execution transfers without moving any data. Compare this to the PyTorch MPS timeline, where the system constantly allocates temporary buffers to simulate transferring data back and forth between processors. By bypassing those buffers, MLX achieves up to 46% faster inference speeds and a 23% reduction in overall memory usage compared to PyTorch running on the same hardware. When the data transfer latency is removed, the performance bottleneck shifts directly to the hardware's internal bandwidth and compute throughput. The second architectural pillar of MLX is lazy evaluation. Writing math operations in MLX doesn't trigger immediate computation. Instead, it builds a dependency mapping of required operations. Execution happens only when explicitly requested via an eval command, which triggers just-in-time compilation, fusing operations into highly optimized metal kernels. This delayed execution approach mirrors the composable function transforms found in JAX. Both frameworks optimize their hardware scheduling ahead of the actual execution phase. However, JAX relies on ahead-of-time static compilation. If a tensor shape changes dynamically during runtime, JAX incurs severe compilation penalties. In autoregressive text generation, sequence lengths fluctuate continuously with every new token. In static graph frameworks, this variation triggers severe recompilation spikes, freezing the execution pipeline. MLX avoids these latency spikes by compiling its directed acyclic graph dynamically at runtime, adjusting to changing tensor shapes instantly without halting the system. By combining dynamic shape support with delayed execution, MLX achieves the composable kernel efficiency of JAX while maintaining the dynamic flexibility of PyTorch. Lazy evaluation acts as a necessary bridge, perfectly molding the computation graph to the precise specifications of the Apple GPU cores before committing any of the actual hardware resources. The ultimate stress test of this unified architecture is running high-parameter large language models locally. Processing a prompt involves two distinct phases. The initial prefill stage digests the input text and is bounded purely by raw compute power. The decode stage then generates the response, one token at a time. This visualization compares those stages. The decode stage is notoriously memory bandwidth bound. Its speed is restricted entirely by how fast the weight matrices can be read from RAM and fed into the compute cores. Because MLX removes the transfer bottlenecks to those compute cores, third-party inference engines like Ollama achieved up to a 7x speedup in decode generation simply by swapping their backend from llama.cpp to MLX. During this generation, the key value cache, which stores the model's context, is allowed to expand natively across the entire unified memory pool, free from the arbitrary limits of a discrete VRAM card. But this direct hardware access carries a severe failure mode. If unbounded KV cache growth exceeds the physical RAM limit, it causes fatal kernel panics. Operating this close to the metal removes the safety rails provided by traditional abstractions. It demands rigorous memory management and strict caching constraints from the systems engineer. Measured. The drive for maximum hardware efficiency introduces a specific, unavoidable architectural cost to the system, inherent non-determinism. To saturate the Apple Silicon GPU cores entirely, MLX deliberately sacrifices strict batch-invariant reproducibility. The variance occurs during thread-level reduction strategies. Depending on the immediate system load and batch sizes, these operations execute in varying orders, yielding floating-point outputs that differ slightly at the decimal level. Because identical inputs can yield slightly varying outputs, MLX struggles to provide the rigid, exact replication required in strict scientific validation. MLX makes a ruthless engineering calculation. It prioritizes raw edge inference throughput over the scientific exactness demanded by traditional academic research. Adopting this framework introduces a definitive business constraint, absolute vendor lock-in to the Apple hardware ecosystem. While recent updates have introduced experimental CUDA support, the library's architecture and performance gains remain deeply tied to the M-series hardware. Yet, the technological achievement stands. A single developer can run inference and fine-tuning on massive 70 billion parameter models natively, using a standard consumer-grade workstation. This localized efficiency scales beyond the desktop. As Apple's unified memory model expands into advanced spatial computing and mobile inference, the architectural footprint of MLX follows. Decentralized AI development relies on a tight coupling between the processor and the compiler. MLX provides the missing software layer required to exploit the full potential of Apple's native silicon.